All right, let's dive right into some of the biggest questions imaginable. What happened at the very first moment of time? What really goes on at the edge of a black hole? Today, we're going to explore these massive ideas through the mind of one of the greats, Stephen Hawking, and see how he completely changed our picture of the universe. So let's start with this quote from Hawking himself, because it really gets to the heart of the matter. What he's saying is that Einstein's theory of general relativity, as amazing as it is, has a fatal flaw. The theory literally predicts its own failure. It just completely breaks down in the most extreme places you can imagine, at the center of black holes, and, you won't believe this, at the very beginning of the universe.
So where does this breakdown even come from? Well, the problem is that in Einstein's theory, gravity is a one-trick pony. It only ever pulls, it never pushes. And when you have a force that is always attractive with no off switch, it leads to these points of infinite collapse. And physicists have a name for that, a singularity.
And this right here is the big bad of cosmology. A singularity isn't just a very dense point. It's a point where the density becomes infinite, where the very fabric of space and time tears apart. All of our laws of physics, everything we use to describe reality, they just stop working. It's a cosmic wall, a full-on error message for the universe.
Now, what Hawking and his colleague Roger Penrose did was incredible. They proved that singularities aren't some weird theoretical fluke. Nope, they're basically unavoidable. They showed that if you just accept three pretty reasonable ideas, 1, that matter has positive energy, 2, you can't build a time machine, and 3, that gravity can get strong enough to trap light, then a singularity is guaranteed to form. There's just no way around it in classical physics.
And this leads us to two gigantic cosmic mysteries. The theory says there's a singularity waiting for us in the future, at the heart of every black hole, a literal end of time for anything that falls in. But, and this is the big one, it also predicts a singularity in our past, the Big Bang. That means our best theory of the universe literally can't tell us how the universe began. That's a huge problem.
Okay, so let's tackle that first mystery, black holes. While studying them, Hawking found something that seemed, well, like a crazy coincidence. He stumbled upon a deep hidden connection between the laws of gravity and a totally different area of physics, the study of heat and disorder. This little clue was about to blow the doors off cosmology.
Okay, now just look at this. On the left, you've got the laws of thermodynamics, heat, energy, disorder. On the right, the laws that govern black holes. The parallels are just stunning. The surface area of a black hole's event horizon can never decrease, just like entropy or disorder can never decrease. And the black hole's surface gravity behaves exactly like temperature. Hawking looked at this and thought, no way this is a coincidence.
And the amount of information, or entropy, we're talking about here is just staggering. A single black hole, just the mass of our sun, has an entropy of 10 to the 78th power. That's a 1 with 78 zeros after it. It's an absolutely mind-boggling amount of information that, according to the old theories, is just locked away forever, lost to the universe. But wait a second, this created a massive paradox. If this analogy is real, if a black hole truly has a temperature, then it has to radiate heat, right? I mean, a hot piece of metal glows. But the whole definition of a black hole is that nothing can escape its gravity, not even light. So how on earth could it possibly glow? The answer, it turned out, wasn't hiding in the theory of gravity. It was in the completely weird, fuzzy world of quantum mechanics. By applying quantum rules to the empty space right at the edge of a black hole's event horizon, Hawking discovered something incredible. They do radiate. They give off a faint thermal glow of particles, which we now call Hawking radiation. It turns out black holes aren't completely black after all. And the discovery of Hawking radiation was the final piece of the puzzle. It proved the whole thing wasn't just a cute analogy, it was real. The surface gravity of a black hole is its temperature. The area of its event horizon is its entropy. This was it, a profound, totally unexpected link between gravity, quantum mechanics, and thermodynamics.
So with that huge win under his belt with his new understanding of black holes, Hawking was ready to go after the other, even bigger monster, the singularity at the very beginning of the universe.
And let's be really clear about what's at stake here. This is the ultimate problem. If general relativity is right about that initial singularity, it means the laws of physics break down at time zero. That means science itself, by its own rules, literally cannot explain our own origin story.
For Hawking, this was just not an acceptable answer. He had this deep faith that the universe had to be governed by laws that worked everywhere and at every time.
So to solve this problem of the beginning, he came up with something truly radical, really out there. He called it the no-boundary proposal. And here it is, in his own words. It sounds almost like a riddle, right? The boundary condition of the universe is that it has no boundary. What on earth does he mean by that? Well, he's suggesting that asking what happened before the Big Bang is the wrong question. It's meaningless, because the universe has no starting edge, no boundary in the past to look beyond.
To get your head around this, picture the old model of the universe's history. It's kind of like an ice cream cone. Time flows up from that sharp point at the bottom, but that tip, that's the singularity. It's a problematic point where everything breaks.
What Hawking's proposal does is smooth out that sharp point. It turns it into a rounded cap, kind of like the South Pole on a globe of the Earth. I mean, the South Pole is the southernmost point, right? But there's no edge there. You don't fall off, there's nothing south of the South Pole. In the same way, Hawking's universe has a finite past, but it doesn't have a singular, special beginning. And the implications of this idea are just wow. It means the universe could have just popped into existence from nothing, in a way that is totally consistent with the laws of physics. That question, what came before, becomes nonsensical, like asking, what's north of the North Pole? The singularity is just gone, and the laws of physics work everywhere, all the time. So, when you put these two huge ideas together, black holes that evaporate and a universe that has no beginning, what kind of reality does that leave us with? It's a picture that's fundamentally different and a lot weirder than the one we started with. We have to throw out that old idea of a clockwork universe, one that's perfectly predictable if you just knew all the starting conditions. Instead, Hawking's work points to a universe where there's a fundamental layer of unpredictability. Because of things like Hawking radiation, information can genuinely be lost, and the future isn't as set in stone as we once thought. And this shift is just perfectly captured in Hawking's brilliant, witty comeback to Einstein. Einstein hated the randomness of quantum mechanics and famously said, "God does not play dice." Hawking's reply, based on his work with black holes, was, not only does God play dice, but he sometimes throws them where they can't be seen. So if the universe isn't a perfect machine, what is it? Stephen Hawking's work leaves us with this incredible cosmos that is self-contained, born from its own laws, but also one where true randomness is woven right into the fabric of reality. He solved the problem of the beginning, only to reveal this deep, beautiful uncertainty about the end. And that tension, that's what keeps driving science forward.